Our goal in looking at this second order differential equation is not just to talk about how to solve it, but also how to think about it in a way that relates it to linear algebra still. Again, being a differential equations with linear algebra class, we do want to relate the subjects. So as a reminder of how to think about it related to linear algebra, you can think of this expression right here, y double prime plus 7y prime plus 10y, as defining what's called a second order linear operator. Really a function between function spaces. If you want to get technical about it, you could say it's a function from C2R to CR as one example of a domain and codomain. You could pick others. Remember, CR means the vector space of all continuous functions that are defined on the entire real number line. Every point in this vector space is a function. What functions are in there? Well, any continuous function. Functions you're used to, t squared, sine of t, e to the t, they're all in there. They're all individual points in this function space. Such a function space by necessity is infinite dimensional. It has no finite basis. Polynomials of arbitrarily high degree are in there, okay? What functions are not in there? Functions that are not continuous, like 1 over t, for example. They're not continuous over the entire real number line. C2 stands for twice continuously differentiable functions, functions that have first and second derivatives that are themselves also continuous functions. That's the domain of this linear operator, and this is the codomain because you take a function that's got a second derivative that's continuous and plug it into this linear operator. That means you can actually take its second derivative for one thing. And you are going to get a function out that is going to be certainly at least continuous. There are other choices you can make here, but this is the simplest choice, you might say. We're after what functions, when you plug them into this linear operator, give you an output of t. That'll be the general solution, at least. And then which one of those functions also satisfies this initial condition, these two initial conditions, okay? So it's good to think about that kind of background. If this were a homogeneous equation, and let's go ahead and write down the corresponding homogeneous equation, where the right-hand side were 0, then what you're really after, in the general solution at least, is the kernel of this second order linear operator as a linear transformation. And the theory says that since this is a second order linear equation, that solution space as a subspace of this has to be a two-dimensional vector space. This is an infinite dimensional vector space, but the solution set, the kernel of this, is a two-dimensional vector space because it's a second order linear equation. So if you can find two linearly independent solutions, two non-zero solutions that are not multiples of each other, then a general linear combination of them will be your general solution. That theory is all in the background. You know, the textbook, being a differential equations textbook, doesn't emphasize all that, but I want you to know it to relate it to linear algebra. Of course, you do your guessing. You guess y equals e to the st. I won't go through all the work, but you get to the equation s squared plus 7s plus 10 equals 0. Can be factored as s plus 2 times s plus 5. You've done this a lot, right? So your two values of s, which would correspond to lambda eigenvalues of the corresponding system, are -2 and -5. But again, like we emphasized last week, you don't actually have to write the system down to solve this. So your YH is a linear combination of e to the -2t and e to the -5t. Those two functions, e to the -2t and e to the -5t, would form a basis for the solution space, not of the original equation, but of the corresponding homogeneous equation. Be a basis of the kernel. They're linearly independent. They are not scalar multiples of each other. And since the solution space is two-dimensional, that means they also span. That means this is a general solution. All solutions of this equation are of this form. But we add the new wrinkle here now for chapter 4. This is starting chapter 4, by the way. We make this a non-homogeneous equation. But just like in chapter 1, you need to guess a particular solution and then add these two to get the general solution of the original. What do you guess? You're looking for functions whose second derivative plus 7 times their first derivative plus 10 times themselves always equal t. No way trig functions are a good guess. No way exponentials are a good guess. How are you going to get t out? You might guess maybe a quadratic, but you don't need a quadratic. You can do it with a linear function, I believe. Let's see. Is that good enough? Maybe we do need a quadratic. Actually, I didn't think about this. Did anybody try quadratic? Do you need a quadratic? No? Okay. A linear function works. Okay. AT plus B. I got confused there. Try a linear function. Take its derivative. Take its second derivative. Here, the second derivative always gives you 0. If this were a t squared instead of a t, then I'd want to guess quadratic, by the way. But it's t. We can get away with a linear function. Plug those things in. Yp double prime plus 7yp prime plus 10yp. What does it simplify to? 0 plus 7a plus 10at plus 10b, which becomes 10a times t plus 7a plus 10b. And we want to set this equal to the right-hand side, t. You want those to be equal to each other for all t. The only way that's going to happen is if the coefficients match. If 10a equals 1, and if 7a plus 10b equals 0, a linear system of equations. You don't have to put it into a matrix. It's fairly simple to solve. A is 1/10. 10b will equal negative 7a, negative 7/10. Looks like b is negative 7 over 100. That look good? So yp is 1/10 t minus 7 over 100. That is one function such that when you plug it into this second order differential linear operator, you get t out. If you add these two things, you get all the other infinitely many functions that give you t out when you plug it in. You have the general solution of the original equation. General solution of the original equation is YH plus YP, just like in chapter 1. So that's K1 e to the negative 2t plus K2 e to the negative 5t plus YP is plus 1/10 t minus 7 over 100. That's the general solution. We know y of 0 equals 1. So that means K1 plus K2. Yes, you just sometimes can't avoid fractions with this stuff, is 107 over 100. Right? 1.07 is fine as well. We need the derivative if we're going to use the other initial condition for the velocity. Y prime's negative 2k1 e to the negative 2t minus 5k2 e to the negative 5t plus 1/10. The initial position is 1. The initial velocity is 0. You can bring that, well, you could actually bring the 2k1 and the 5k2 to the left side. 2k1 plus 5k2 equals 1/10, or maybe it'd be good to write that as 10 over 100, perhaps. That might be good. Now, to finish the problem, I just need to solve this system of linear equations. These are long problems. I know you may not have finished in the time I gave you. Can I do that in my head? Maybe multiply this equation by 2 and subtract this minus this after multiplying by 2, so that the k1s cancel. If I do that, the k1s cancel. 2k 2 minus 5K2 is negative 3K2. Doing it in my head here. 2 times that is 214 over 100 minus 10 over 100. It's 194 over 100. Look good so far? Tell me if I make a mistake. K2 is, let's see, is that divisible by 3? No, it's not. Negative 194 over 300. So K1 then, using, say, this equation, 107 over 100 minus that'll be plus 194 over 300. That's 321 over 300 plus 194 over 300. Looks like we got what, 515 over 300, which would reduce to what, divide both top and bottom by 5. What do we get? 103 over 100? No, over 60. I think we have to stop there. I think that's not reducible anymore. Oh, yeah, thank you. It's easy to make a mistake here. Thank you. So that's a 204, which could be reduced. I guess I could have reduced it before as well. 204 here, 204 here, 525 here, 105 here, and it reduces further then to 21/12 and reduces further to 7/3, 7/4. They have not made a mistake. This one reduces to negative 102 over 150, negative 51 over 75. And those are both divisible by 3, but okay. We can go further. Negative 17 over 25. Okay. That's K1 and K2 if I had not made a mistake. And then you plug them back in here to get the final answer. So yeah, there's a lot of work. I didn't really give you enough time to finish it. So if you uploaded what you had, it's fine. But really more important to me was what I was talking about at the beginning, as far as the math goes, at least. As far as applications go, that's important too. That's a second order harmonic oscillator. You could think of it as a mass on a spring with external forcing function T. What kind of external forcing would act like that? Nothing I can really imagine, because it's just saying the force just keeps increasing. It probably would cause the spring to break in reality. Maybe for a short amount of time, you could do an external forcing like that. And what would cause it? I don't know. Wind that keeps increasing. Does that sound reasonable? It's like in a wind tunnel or something, and mass going back and forth in a spring in a wind tunnel, and the wind just keeps getting higher and higher. Of course, there are complexities that come up in that kind of situation, like the turbulence and stuff, right? You're in fluid flow, some of you. Turbulence or something probably would make it more complicated, but maybe as a rough approximation for a small amount of time, maybe it wouldn't be too bad. Okay, but if it got too high, the spring breaks. So, should think about reality too.